So yes, good afternoon to one and all. So any doubts in the last class? Any queries? Have you practiced?
No, sir.
Gokul, you have sent me some error, no?
Yes,
Have
sir.
you sent it to my mail ID, that error?
Yes, sir. I have sent it. Right.
Where is that message?
The cluster value. I can't change the cluster value.
You must compute and read view factors or use existing view factors. No, you have not saved that file?
Write.
That
Saving
means you
means
have not.
writing.
Yes, yes, yes.
I think I have done that. I will.
First, what it was saying is you must compute and read it. Compute and read view factors or reuse the existing view factors. That means you have not done. Please disable S2 model to continue without using view factors. That means you have not saved. I think so.
Okay. I will try it.
Okay. This is the thing. And any queries? Anything else you want to know? No, sir. Till now we have not practiced, sir. Is there any person like that? You got 2 days time, man. More 2 days time you got it. Sir, you get 2 days time, but we have batches, sir. Other batches also we have, sir. So in the last class we were discussing about this modeling radiation and natural convection, and so in the last class to where we have discussed about modeling radiation and natural convection. Today what we are going to study, we are going to study about the transonic flow of an external compressibility. Transonic flow of an external compressibility we have, so that we are going to study it. What is mean by transonic flow? There are different types of flows: transonic flow, hypersonic flow, supersonic flow. There are different types of flows. So first I will show you this, you will get some idea. So here you can have this. So different types of flows we have. So based upon that, we'll classify it. Okay. On what basis you will define this different types of flows we have depends upon the Mach number. So if Mach number is greater than 5, then we can call as a hypersonic flow. Hypersonic. And next one is we have Mach number which is greater than 1. Okay. So that Mach number which is greater than 1, that we call as supersonic flow. And here if Mach number is equals to 1, that is we can call that as a transonic flows. Okay. So if it is less than 1, that we can call as subsonic flow. Sir, how you define this Mach number? The speed of the object by speed of the sound. Speed of the object by speed of the sound. So what is the speed of the sound? Anyone? What could be the speed of the sound? Answer. Please respond. What is the speed of the sound? This is a general term I am asking.
So it's equal light speed 3 Newton per 8. 3 Newton per 8. It's equal, I think, light speed.
I need other persons also. Yeah. No one is hearing my voice or what? You are able to hear my voice or not? There are total 6 participants. No, you can hear Kishore, Gokul, Shanvas. You are there, right? You can hear my voice, right? Santosh. What
Sir,
could be the speed
yes,
of the
sir.
sound?
Sir, it is around 300 meter per second, 1,200 kilometer per hour.
Okay, so that you can take it as, for example, so this is how you define this Mach number. So Mach number is defined as Mach number is defined as speed speed of the object. Speed of the object. Okay, so that too speed of the sound. Thus we are going to calculate. Okay, so now usually the speed of the sound will be in terms of how could be. So this is like approximately it can be vary of 314. Okay, 314 approximately 314 to 316 meter per second. Meter per second. This is standard you have it here. 314, I mean 314 to the 316. So between this range, the speed of the sound will be varied. Now, as per the the known parameter, as per the known parameter, we are going to use it. So from this, we know the speed of the sound. We know the speed of the sound. If you know the Mach number, if you know the Mach number, we can calculate the speed of the object. We can calculate. Now, on what basis you will calculate this Mach number? The Mach number is calculated on this various. So now it is like Mach number is greater than 5. Greater than 5, we can call this as a hypersonic. If it is greater than 1, that is between this range, that we call as supersonic. If it is equals to 1, then we can call as transonic flows, mostly for aerospace components. So this is like super jet engines. Super jet engines we can have. Okay, and which is less than 1, this we call as subsonic flows. So that way we can classify it, right? So now I hope you understood what is meant by transonic. Now our example is transonic flow of a external compressibility. Transonic flow of an external compressibility we are going to calculate. Now first I will make you to understand. Here we have a airfoil. If you consider, this is a airfoil. So the whole length of this airfoil is 1 meter. And now what happened is, what here I've just put it here. Now here we have this airfoil. Now over this region, the whole length we have. Now the air particles are hitting this region. Now the air particles are hitting to the front portion of this area. The air particles are hitting this front portion of this. Okay, so these are the air particles. Now it is moving some velocity which Mach number of. So already they have mentioned this Mach number is 0.8. Mach number is 0.8. The area which is the air is attacking with an angle of 4 degrees. The air is which is hitting this front portion with an angle of 4 degrees. Approximately 4 degrees which is hitting this front portion. So what I do is I will take instead of alpha 4 degrees, then how I have to apply this 4 degrees, sir? So what I do is I'll apply cos 4 degrees value. I'll apply cos 4 degrees, and also I'm going to apply sine 4 degrees. I'm going to apply that. I can get it, no, the direction I can get it here, cos 4 degrees and sine 4 degrees I'm going to apply. First, discard. Now what I do is I'll read the problem description. The problem considers the flow around the airfoil. It is an angle of attack that is alpha 4 degrees and a free steam Mach number which is of 0.8. The flow is transonic as they mentioned and has a fairly strong shock near the mid chord, which is which distance from here, x by distance from here, it is 1 meter, right? Exactly 0.45 mid chord, that is of 0.5 distance on the upper suction side, and the chord length, this they have given the shock near exactly 4.5 distance, and the chord length is 1 meter. You can see. Now what you're going to predict in this study, sir? What you're going to learn in this study? So the purpose of this tutorial is to compute turbulent flow past a transonic airfoil at a non-zero angle of attack. You will be using the method called Spurlart-Alam's equation, SA equation, or you can also call as, this is one equation which is to find for aerospace components. Okay, you will be using this Spurlart-Alam's equation or turbulence equation you can call. Okay, so this, using this equation you are going to find. Now what you are going to demonstrate in this, so how to solve the of compressible flows, how to set the boundary conditions for aerodynamic problems, how to solve this Spurlart-Alam's turbulence model, how to use this FMG. What is mean by FMG? FMG is nothing but full multigrade integration, full multigrade integration you can call, full multigrade initialization. So using this initialization we are going to solve. So for what purpose you are using this FMG? To get a better values we are using this FMG method. Okay, so calculation solution using pressure based coupled solver using physio transient, and use force and surface monitor to check the solution convergency, and check near the mesh resolution by plotting y plus, that using we are going to calculate. So what is mean by this Spurlart-Alam's model? What it is going to do this? So it is designedly, or it is specially designed for aerospace applications, which is involving as wall bounded flows on a fine near wall mesh. Okay, so what using this method you are going to study? Designed specially for aerospace applications involving wall bounded flows or fine near wall meshes. Options to be included: strain rate and also K epsilon terms, which is improve the prediction of volatile flows. Volatile in the sense the irregular or uncertainty flows we can go. What is the benefit of that? Economical for large meshes, suitable for midly complex, that is quad 2D, external or internal flows and boundary layers flows under pressure gradient. Example: airfoils, wings, aeroplane, fuselages, missiles and ship hulls, where we can use this Spurlart-Alam's model. Limitations: perform poorly for 2D flows, free shear flows, or strong separation, because it is not perform very accurate for 3D models. So we can perform for 2D models. So what is mean by FMG? As I was talking about, full multigrade initializations can be used to create better initialization for flow fields. What do you mean by flow fields? How the air particles are moving in the airfoil, that to get a better results we are using this method called FMG. So we have to know, in order to activate this FMG method, we have to use this combine. So all initialize, FMG initialization, we have to give this combine. Then only the problem will be solved as a FMG method. So FMG is computationally inexpensive and faster. Euler's equations are solved with first order accuracy and coarse level of meshes. It can be used for both pressure and density based solvers, but only in the steady state, not in the transient cases. Okay, so you can give this settings once the problem is solved. I hope you understood 5 to 10% what they have given and what we are going to predict. I hope it is clear. Everyone, 6 of you. Kishore, Anurag.
Yes, sir. Yes, sir.
Yes, sir.
The problem
Yes, sir.
description you are clear?
Yes, sir.
Yes, sir.
Okay. So what we want to find and what we are going to find, I mean what we are going to see the results, that we are going to see it. So I'm
It's
going
only
to,
for 2D, not for 3D.
we can solve the 3D, but it will have poor results. We can solve the problem, but it will have poor results as it is mentioned.
Yes,
So you can take it, no, fluid flow fluent, I'm going to take it. So mention that model name as transonic flow, or yes, transonic flow, you can take it. Okay, so I'm going to take this as transonic flow. Now from the hands-on files, I'm going to take the mesh file, right click here, import, browse. I'm going to take this airfoil, no, example, the mesh file, I'm going to take it this. So go to the setup, I'm going to use it this. So go to the double precision, I'm going to use it. So just fit it. Now you can see this is your external compressibility total thing, and this inside your here, this is your airfoil. Sir, why they have been designed in this? You will be getting a doubt, because in the space we cannot put it, so we have to arrange a boundary so that inside we are going to give some volume of pressure we are going to give inside. Okay, so inside is your airfoil. This is your airfoil. This is your airfoil. Okay, this is your airfoil type, but this is your boundary of your airfoil. Okay, so inside we are allocating some pressure to that. Now if you see the elements over here, the elements is too big. If you keep on, no, you see the elements over here is too big, so definitely one criteria is going to fail, you know, if you go with the checks. So what it was showing, the error, the mesh contain high aspect ratio, quadrilateral, hexahedral and polyhedral cells. The default algorithm used to compute the wall distance required by turbulency model might produce wrong results in these cells. Please inspect the wall distance by displaying the counters of wall cell distance at the boundaries. If you observe an irregularity, we can recommend to use alternative algorithm to correct the wall distance. That means, what is meant by aspect ratio? The first question is, what is will be aspect ratio? So aspect ratio, I think the people who are good in hypermesh, they knows what is meant by aspect ratio. So when you go with, so we know that the perfect elements are quad, this is your quad element, and this is your tria element, and these two are ideal elements. Sir, how you said that is a ideal element? When these all sides are equal, all are in equal sides. Okay, and it is also perpendicular within these corners, that we can say is a perfect quad element. Then sir, how could you say this is a perfect tri element? The angle between this all three sides is 180 degrees, I mean 60 60 180, so that is of equilateral triangle. We can say that is a perfect tri element. Now then, how could be, what is mean by aspect ratio? That is my question. What is meaning of aspect ratio? How you know, how you classify this? So it is defined as
Trading
maximum.
side fluent. Ansys fluent. One.
Gokul, please mute your voices. So how you define this aspect ratio? It is defined as maximum edge length to the minimum edge length. maximum edge length to the minimum edge length. So then how could be the maximum edge length? Now if you take, no, we know that if it is aspect ratio is equals to 1, then it is a perfect element. Then how you said, sir, how could you say, if you take, no, this length is, for example, you take this is 3 units, as you give a condition like this all are equal. Now if you take this is the other 3, so maximum edge length to the minimum edge length. Now when you take these two ratios, 3 by 3, so the ratio it is equals to 1. The ratio is equals to 1. Then that we can say is the perfect element. Then how could be the failure element? The same cases, the maximum edge length to the minimum edge length. The ratio if it is equals to 1, that is a perfect element. Then how could be the failure element? So if the elements are which is large in the length in one side, and no, here also which is large in the other end also, this will be the failure elements. Definitely this aspect ratio is going to failure. Suppose this length is, for example, you consider this is some 10 units, okay, and this is like 1.5 units, 1.5 units. This is 1.5, and approximately this is 8 units, and this is of some 2 units you have. This is of 2 units. So maximum edge length is 10. When you take the ratio of 10 by 1.5, so approximately it is 9.5. You will be getting 9.5 something. You will be getting here the ratio. Then definitely this good element will be a failure element. This element is a failure element, and this element is also failure element. Sir, up to what range the industries can be acceptable? Industries can be accepted up to the range of 1 to 5 they can accept. Between the range 1, 1.5 to 2.53 up to 5 they can accept. But if it is more than 5, that is a failure element. If it is less than 1, that is a failure element. So the element should be present between these two range 1 to 5, the element should be present. Now here also the same concept, you can see it. Now what happened? It is getting aspect ratio is getting failure. You can see this elements. You can see this element. I think you can see these elements, and some elements over here you can also observe here.
Yes.
Here also. Can you see that element over here? So this element is getting failure. It is showing a warning messages. So then how, sir? How I have to remove this error, sir? How we have to remove this error? So such type of errors, how we have to remove? So here you can go with here mesh reorder. You can just make a mesh reorder these elements. Mesh reorder, reorder. You can go with here domain cases. You can just, so how much it has been reduced. The bandwidth is reduced to 69%. Okay, it can be reduced. Even now, if you go with checks again, you will show this error. But at least we are, we are reducing those errors. Like 70% we have been reduced. Okay, 69.01, that is 69 point we have been reduced. Okay, so how we have to reduce this error? Mesh reorder, then you can go with a domain. Okay, so this way we can go with that. Then so what is the next step we have to do? So the next step is, it is a pressure based, so report the quality. I'm not going to scale this object because accordingly it was, so go for scale. So I want to view the lens into meters. No, it is in the fine. Okay, this won't be the problem. I'm going to use it here. Then report the quality and display. So it is a pressure based absolute steady state planar. I'm going to use it this. Okay, so next case is go to the models. I'm going to use it multi-phase, not multi-phase. Here you can go with your viscous. In that SA method, Sperlat Almaras equation. No, you can see first equation I'm going to use it here, right? So it is you can go with here. So that too, different irregular flows, vorticity based or strain or vorticity based you have. I'm going to use the second option. I'm going to use, that is irregular flows. I'm going to calculate. So try to give okay, right? So once we've been defined. Now the next case is which what things are going to flow inside. The air particles are flowing inside. So that I want to give it here. Sir, how do I activate, sir? Go to the materials, air. So that is an incompressible air it was. So go with edit. So from this you can change type to incompressible. Incompressible ideal gas. I'm going to use it here. Okay. So this parameters I'm going to change it, and that to specific heat is I'm going to use this values. Specific heat, how much it was? Okay, 10. Default cases I'm going to use thermal conductivity, which is having 0. Okay, 242, it's fine. And next case is I'm going to use viscosity is I'm going to change it, that is of Sutherland. You can take it here. I'm going to take this Sutherland. So what three parameters we have here? One is reference temperature and effective temperature. The three input parameters I'm going to use it. That is 3. Okay, you can use it here. So automatically when you activate this viscosity, energy is, you can see the note condition. Whenever you note, enabling the energy equations are required by the material of density method. So automatically, previously we have not activated the energy. No, automatically now it's showing automatically enabling this energy equation. So try to close it here. So go with cell zone conditions, fluid, so which air is passing, that have been given here, right? So that we have given. And what could be the next case? And this I said, this is your red color which is having the boundary, that is your pressure par wheel variable. So go to the boundary conditions. Already when you click on this, sir, what is meant by wall top and bottom? So this I will make you to understand, because this is very important in order to understand this problem. Go for general, display, undo all this. So which is wall top? Wall top first I will make it, this is your wall top and wall bottom. Okay, so wall top and bottom, and pressure far field variable, I'm going to display, that is your boundary. The red color is your boundary. And the next one is the interior mesh, so display that interior mesh. Okay, so using this all inputs, now you understood which is wall wall bottom and wall top, what is the pressure field. So go to the boundary conditions. In that, wall top is wall itself, wall bottom is wall, both are walls, and this is pressure far field variable. You use this pressure far field variable. Okay, so type we have to mention, sir, if this is mismatching, the problem will not get solved. We have to decide it from what, either is a pressure inlet, pressure outlet, what this is. By this itself the system can understand what variable you have to use it. So that is pressure far field variable. Okay, so that I'm going to use it. So next, for example, I'm going to use it. Now sir, then how I have to define the inside pressure? So go with, click on this pressure far field variable. So then you can go with here movement, but I doesn't know x velocity and y velocity. I know only the Mach number. I know only which cases, angle of attack, which is of 4 degrees, we know that. So using that, how do I define this, sir? So I'll go with here x direction. Okay, so this, because the air particles are hitting this region, right? So that what we have to do is, I'll go with cos 4 degrees and sin 4 degrees. X is positive direction, I'm going to take it. So go with I'm going to take calculator, because I'm not good at in that. So trigonometric sine, okay, 4, I'm going to take it this. So which is having sine 4 degrees, how much? 0.0697. So that I'm going to take a sine value. Okay, so 0.069, you can take 69, how much? 69756. 756, I'm going to take it. And then how could be the cos 4 degrees? Then you can put it here, 4 cos 4 degrees, which is of 0.97564. So this I'm going to take it, 0.997564 we have. And what could be the Mach number? Mach number they have given as 0.8 is the Mach number. Okay, so turbulent viscous ratios, I'm going to take the constant value of 10. Okay, so which is I'm going to take it here. And the thermal, which is of 300 degrees, I'm going to use it this. Okay, so once you define this, try to give okay, that we have given. And then what could be the wall temperature and all that? So here I'm going to take it, boundary conditions, operating conditions, you can go with here, which is having pressure of 1 bar. Okay, I'm just saving this for future reference. I'm saving this project. Sometimes what happens, if you change the inputs, it is going to be closed automatically. So I'm saving my future reference desktop. I'm going to use it. Here I'm going to use it transonic. I'm going to save this. So try to save it here, right? Yes, it has been saved it. So then I'm going to use it. Solutions, yes, dynamic mesh I'm not going to reference. Method solution controls I'm going to use it. So solution methods I'm using coupled solver. Okay, sometimes using automatically it will close it. Not in your software, but sometimes it is going to close it again. Again we have to start from the beginning. Not again we have saved, right? Not a problem. You can cross check that. Anything is missing, we can cross check that. Yes, it has been saved. It's the boundary conditions, pressure field variable, you can see that. Okay, it is not missed. You can have it here. So go with solution methods. So here I will use coupled solver. Okay, and that is CDO transient, and because turbulency we required, that I am going to second order, and energy it is not yet required. Okay, energy is not yet required. So if it is, let it be second order. Movement second order, yeah, let it be this. Okay, so thus we've been saved it, and once we have done now, and go to the solution controls, and energy we have, turbulent connectivity we have used. So density, how much it was? 0. Yes, so density I will be decreasing it. It is not 1, 0.5 I am going to use it here. Okay, and turbulent viscosity ratio, how much we can have? It is turbulent viscosity ratio. So it is viscosity. This is of 0.95. I'm going to use it here. Okay, so those parameters I'm going to change it here. So if it is 1, that is will be 100%. Now I'm not going to use that 100%. So go with your monitors. So which area you want to predict your results? In which region you want to predict the results? So go with here initialized. You want to give any monitors, you can also give that, create it. So what things you want to see? I want to see this. Which thing you want to see? So that I will go for here. Flow rate, you can see flow rate at which region? Pressure at this area, you can see that. Okay, flow rate at area of pressure region, pressure variable, far field variable at this region. I want to check it here, right? Even I want to write it there. Flow rate I want to see that. Okay, so apart from this you want to look at, you can also see that. So then go for solutions. I'm going to initialize this, right? It is going to be initialized. Now I'm going to give a command. We have to use FMG, full multi-grade initialization, to get better flow field variables. We have to use, just give click on this command prompt, just click out in this command prompt, just give enter. So what command you want to give, sir? So just make a note, please solve. Okay, just give command as solve dash initialize I. If you miss one letter also, it is going to be shown as a wrong. I am just giving it flow, INIT I A L I Z D, initialize set minus FMG and initialization, set FMG initialization INITIALIZATION. So this I am going to use solve initialize set FMG. So initialize, just give enter. So customize your FMG initialization, set number of multi-grade levels. So how many levels you want to maintain? 5 levels. I'm going to default it is 5. I'm going to use 5 levels. So reduce the level 1 0.5. How much you want to reduce? Let it be 0 default. So number of cycles in level 1, I'll put it to 100 cycles. Okay, enter. In level 2 also, how many 2 you want to maintain? There is 50, I'll put it to 100. Okay, so that is 100. So level 3 is 0. No, level 3 is 100, just give enter. So level 4 is 0.0, that is also 500, enter. Okay, so in the level 5 it was how much it was showing. Okay, so it is showing 0.1. So in the level 5 also 500, I'm going to use it here, right? So set FMG with number of 0.5%. You want to use it, that? Yes, enter. So it is a, it was showing this enable FMG is a verbose. Yes, it is it is irregular type of thing. I'll go with yes. I'm going to give yes, enter. So now what it was showing, so we have given this yes. Now again we have given write a command. Now we are going to initialize this. So previously we have setting, now we are initializing it. So again you will give a command again, sol. You see the difference here, you observe it. So what we give it, we sol initialize set FMG we are doing, set FMG we are doing, but here what we are going to do is I'm going to solve with that, SLO we solve dash initialize ALIZ initialize set. Previously we used set, now I am not going to use set. Okay, FMG initialization I'm going to use TI LIZATION. So this I'm going to use it, enter. So enable FMG right now. Yes, I want to enable right now. Just give enter. Yes, now it has been initialized. Then so you can go with this all. We can go with here. Okay, so from here I'm going to see that you can also calculate reference values. You can also take from pressure. What are the inputs we have given here? You can see here area and all the stuff you can see here. So now, sir, what is my intention? I want to find the coefficient of drag and lift of this airfoil also, because on this basis itself we can find it. Now I want to calculate the coefficient of lift cases. Sir, how do I do that, sir? So then go for here, monitors. So here you can try to create here drag, lift and movement. You can find it that. So just go with here coefficient of drag cases, CD value you can calculate. Print and console, write, even I want to write it, which region, both the top and bottom and top, I want to calculate the coefficient of drag. Okay, so this I want to predict it. So just you can go with here at which region. So this is a distance, we can locate at the distance. Now it's showing 1, I don't want to have x and y vector I want to look at. So this is at a distance of 0.9976. now at y distance, so this I am going to give y distance. So 0.06976 you can give here. Distance from here to here, the total is 1 meter, and here we can use 0.0976. I am going to use it this area, and I am going to use it coefficient of drag we give, and also I am going to use lift position. The top region lift. Okay, I want to use it that. So that to print and console at which region, the both region, wall top and bottom, at which location. So this is also I am going to give 0.069, this is the location, and y distance is I am going to use 0.9976 at this location. Sir, can I change? If you know the exact distance, you can give it here, but approximately I am giving here this distance, but the whole x distance I know 1 meter. Okay, so that I want to know exactly over here 0.05. You can go, you can have it here. Okay, so just you can try to, okay, and even I want to have coefficient of movement over this region. This is coefficient of gravity, coefficient of lift, coefficient of drag, coefficient of lift, coefficient of movement downwards, and coefficient of thrust, or we can have this coefficient of movement. That to print and console. Even I want to write it that at which region. So I am going to find this is at location of 0.25 meters. Okay, so try to give, okay, this inputs we have given. Now, so what things you want to see that, I'll go with here counters. So you can see Now I want to see, sir, instead of this, no, sir, anyhow we'll get a results here, we'll get it, no. But what is my intention is, I want to see the results exact. If I click one point, I want to see the counters of the region. I want to see that. Sir, how do I get it that? So what you can do is, you can go with, surface point. I want to create a point at it. Surface point at which region? So usually, if you know the coordinates, you can give the value. First, I'll go with the two ways. One is coordinate method, or general by clicking here, I will go with that. So 0.4 is, you can go with here. How do you create? So by, I'll go for identification, I'm giving by coordinate. I'm going to create. So if you know the distance, you can know by coordinate. I'm giving it. For example, at a distance of 0.5 region, and this y distance is 0.051 location, I'm going to locate it. So by coordinate method, just try to create it. The point will be created there. Now this time, what I do is, by manual click you can go. So 0.5 is by manual click. By manual click. Manual click, I'm going to use it. Sir, how do I click it, sir? Now select a point with mouse. No, you can click it here. Just click it one, right click. No, you can see a red color symbol which is highlighting over there. Guys, have you observed this area? Okay, you can click it over this point, this region. You can click it here. So automatically it locate, no, existence and y distance. Guys, is that clear? Everyone?
Yes, sir.
Okay, Mohammed was there, Ranjit, Gokul, yeah. So once you done, try to create over there by manual click and try to close it here. So just zoom out here. Both 2 points will be enabled, no? 2 points will be there. By manual click and by coordinate method too. Sir, how do I check it? Now, if you go with here general display, both the things will be there. By manual click and by coordinate, both points will be there. You want, you can just click it on that, it will be display there. So this way we have it. So now I want to see the results over there. So go with here. Even you can go with the monitors, and I'm going to create it. Okay, so you can just create that region. So what you want to see it? So by manual click, no, both are there. By manual click or by coordinate. For example, I go with by manual click, print and console. What results you want to see? So I want to see that velocity. I want to see that exactly that region. I want to see the velocity. Okay, by manual click point, no, I want to see the velocity. So you can go with here. That is a vertex point, right? You can go with vertex maximum. So I want to see the velocity variable, velocity magnitude, and try to give OK. So this many inputs we are going to calculate in the problem. Okay, so how many iterations? Approximately you can go with here some 200 iterations I'm going to calculate, because so go with here. I'm going to use number of iterations. For 200 iterations I'm going to calculate the solution. Try to calculate it. So CD value, coefficient of lift, coefficient of movement, everything it is going to solve it. This is CD value. You can put it to 3 or 4 windows. You can know. You can put it here. Coefficient of lift, movement, and all you can see. You see, it has been get converted 145. You know, you can see it 145 results. It has been converged. So you can put it into one window. So this is what it was, velocity. You know how much velocity it is having. And by manual click point, it was velocity is having approximately 392. 392.5 it was there. Okay, so this region we have 392.5 it was there. Now what could be the drag positions? So 0.1 you have 0.1 maximum, and what could be the lift position, which is having 0.5. I mean the maximum is having 0. Approximately 0.79 it was there. Okay, and movement, this is also like 1.11 it was there. So sir, can I see the results? Yes, we can see the result. We'll go to the results and we'll check it the results. How could be this? So first case is graphics, counters, setup. So what I want to see the pressure, you can just go with here. So this is about the pressure. Sir, what could be the velocity? You can see the velocity. You can see the velocity. Okay, sir, by manual I want to see by points. No, you can plot the graph also, because already we created points, right? We can see that by coordinates and we displayed, right? So this way we can plot it here, right? This how we can have. Okay, so you want to see the shear force and all that stuff, you can go with here. Even you can plot it. How do we plot it? So go with plots, xy plot, create it. So how you want to plot it? So I want to see the pressure coefficient. So I want to see the pressure coefficient. Here you can go with here nodal values. So what you want to see is I am going to use it here. So pressure, here you can go with here instead of static pressure, directions I'm going to use it. At which region you want to see that? So along y axis, this I'll put it here in 0. It should be in 1. So you can see there. So you can have it here and try to which region you want to plot it. So I want to plot it for both the cases, wall top and bottom. You can plot it here. So which is showing in the this area, because we should give in the proper order. Might be how much we have the velocity, which is we can go with here. So you can put it here along, you can put it 0 and this could be 1. Might be we can go with here both the cases. How we have, you can see here at white color indicates at the top region, red color indicates at bottom region. Wall top is red and wall bottom is white. You can see white region. What is the static pressure we have? So we can go with here. Okay, so this you can go here. So and I want to see instead of static pressure, I'll go with your pressure coefficient. This you can go with here. So how you have. So this is a pressure coefficient, how it has been getting changes. So can I see for shear stresses? What are the stresses we have? Pressure, I can go with here. Wall fluxes you can see, wall shear you can see that. So how it is the shear forces. Okay, so you can see with respect to distance, the total the chord length is 1 meter. From here you can see. Okay, sir, what could be the Mach number? Can I see the Mach number, sir? We can also see with respect to Mach number also. Sir, how do I check it? So wall fluxes, in that you can go with here. Total surface number, you can see from here. Turbulency with respect here. Turbulent viscosity ratio, turbulent kinetic energy. Turbulency I'll go. Wall y plus effect Prandtl number, velocity angle, we have Mach number. We can go with respect to Mach number. We can give that means 8 e power minus 0.8 over the top region. See 8 e power minus, that means 0.08. 0.8, 0.7, 0.61 with respect to that we have. Right? So this way. No sir, I want to have at the top region itself. You can try to plot it there. The top region, how much it was, no? From here, the distance with respect, exactly the distance of 0.4, how much it was? Approximately, 7.9 we can decide, 7.9 or 7.5, 0.75. 0.75 at a distance you can just decide that. No sir, you want to load, you can save this file, you can save it and you can decide it. No sir, I want to decide by manual click, no, at that point, no, you can see that point, at that point how much it was having. By you have given the manual click, right? So at that point how much it was? So 1.28, approximately this 1.29, you can 1.29 you have there at a distance of, you can see. No sir, by coordinate you have given, no, by that way. So this is where you have approximately 1.4 there you have Mach number, right? So this way you can plot it. Understood? Any queries you want to ask, please let me know so that I'll clarify your doubts. No sir, we have to practice once and we'll come back with the doubts. Question itself me and answer also from my end also. Kishore,
Yes, sir.
any doubt?
No, sir. At present, no, sir. I will practice it and I will ask it out, sir.
Okay. Then what about Gokul, Shanvas, Ranjit, Mohammed?
We'll try it, sir.
You will try it?
Yes,
Okay.
sir.
No, sir. No, sir. We'll try the model and then we'll let you know.
Sure, that will be good.
Hello, sir. I have not received that PDF file and mesh file.
Which one?